Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah. Okay, good morning, everyone. It's a great pleasure to have Neil Campbell here from the University of Bath. It's a little bit of a reunion. There are at least 4 generations of Roberto in the audience, and including the speaker. So I'm very excited to hear what Neil's going to talk about today on generative models of shape and appearance.
Cool. Thanks, Jamie. I cut a load of slides about how to motivate why you'd want to use a generative model, so we don't have to go through that, because I thought for you guys it would be a simple thing. So I'm not even going to go through the offering the many advantages, but just the particular advantages that I'm interested in. And it's to go actually the other ways. Often at the moment, we're going from computer graphics to try and help us with some vision. And I'm saying, let's get a load of training data of images or shapes, perform some unsupervised or semi-supervised learning, and then use that in a new context going back the other way. So I'm more interested in, recently in some applications in graphics, how we can help people in graphics by using some vision learning and building some models of this sort. So there's sort of 3 things I was going to talk about today. A generative model of fonts, so this is more shapes or human man-made shapes. I consider fonts just a specific example of a set of shapes that obey certain rules. I'm not crazy about fonts. Generative model for appearance, which is work just come from CVPR. And there we're targeting sort of deformable part-based visual objects, things that don't conform to normal simple subspace parametric models. And then really briefly, just a sort of illustrative application of something we brought some of these ideas together with recently, just come out in the Computer Graphics Forum on how you could make sort of an artist tool using this sort of training data to help build some models. Cool. So starting with the fonts. So we started looking at this, and I found very rapidly what everyone already knows, that designing or editing fonts is really hard. You have to be an expert typographer. There's loads of rules that you have to learn, and you have to use really bizarre GNU complicated software or pay Adobe a large amount of money to make them. And you're basically given a curve editor and told to make curves that are only fonts. So if you're me, the everyday user, what can we do? Well, we've all got access to a large collection of fonts on our hard disk. And so can we use some kind of unsupervised machine learning to try and help capture the rules that we know are encoded in these font designs so that we don't have to learn them all? So if you like, the motivating example would be if we have a standard font editor and I pick a point on there, a set of outlines are a set of Bezier curves. If I grab a point and move it around, we get something like that. And now I think we're all agreed that's not really a valid font anymore. So if we had an intelligent font editor and I grabbed that point and pushed it down, maybe something like this would happen, where we know that like stroke contrast is a thing that's preserved under font. So if the base gets thinner, my stroke contrast is getting thinner, so the top corner should get thinner. And then if we had a really intelligent font editor, as I grab that and push that down, then perhaps all the other glyphs would automatically alter themselves in a similar fashion to keep themselves consistent with the edit that I'm making. So that's a sort of just a motivating example of why. And this is very easy to achieve if you had a nice generative model of system. So why should we build some generative models? Cool. So obviously, from a machine learning point of view, these rules are, well, if you take the space of closed curves, you've got a massive set, and not all of them are fonts. So if we consider as a representation that maybe we go around our curve and subsample it at a set of points, so give a polyline representation, and then of course we have all these interdependencies, which is giving us a much lower dimensional space in reality that's occupied by fonts than the general space of closed curves. So there should be something we can learn there. And there should be some low-dimensional manifold that exists. So that's something we should be looking out for. Like people have worked before on just assistive font design, So there have been some work on parametric methods before, including the Metafont system, which looked something like this, where you would make explicit you sort of hand-code a generative model of the fonts with a set of rules, and it would you could then vary a couple of the parameters. So he's got some parameter sliders on the width. Of course, some of these are valid, would create valid configurations, some wouldn't, but it was a bit complicated, not the best of interfaces. There are industry standards for doing this, and they're called sort of like Adobe multiple masters. So you have a font file that actually encodes a couple of different states, and they exist as a linear interpolation between those states, or trilinear interpolation. But the problem is you've got to design all your fonts like this to be where all your Bezier curves and their control points are all in exact correspondence. So just linear interpolation in the curve space will create your fatter or your thinner font or something like that. So that's quite a lot of work to put all these in alignment. And so our approach is very similar to this kind of thing, but we're saying we just take the existing fonts from your hard disk that aren't in alignment at all. We don't require anyone to go in and edit all the curves to put them in alignment. We find the correspondence automatically. And also we do more intelligent, inverted commas, interpolation, extrapolation, where we're finding the probability on the underlying manifold from the fonts themselves. So we don't just, it's not just a linear interpolation between some matched points. It's a sort of nonlinear interpolation and extrapolation based on data. So in general, sort of data synthesis and hinting, there's lots of work on, we're not going to talk about font hinting and things like that. So people have been working on sort of other tangential topics related to fonts. There's also browsing structuring of fonts, and again, I'm treating these more as shapes as opposed to caring specifically that they're fonts. So obviously there's a lot of work on shape matching and shape interpolation. And the main thing I'll say about this is that a lot of work at the moment is being done in the graphics community, certainly, with pairwise matching techniques. And these introduce problems when you're trying to build such generative models. So the other sort of subtext to this, which is on the next slide, is the representation that you choose to use and how you choose to do the matching, I think, is very important. And there's also sort of other works that show shapes with templates and things like that, like dolphin paper and things like that. Having these sort of models allows you to do lots of useful things. So what I would call the universal parameterization is the answer to the sort of pairwise matching system. So global matching, when I mean global as in across all my fonts as opposed to global optimal, that we have a representation where you treat each font as a polyline, and we try and find in one, so we treat each glyph as an example of it, we match outline to outline, and we do them all at once so that they create a vector at the end where each point in the vector is in correspondence across all of the fonts. So this creates a huge parameter vector, but is uniquely parameterized across the whole space of the fonts. So if we had pairwise matching, I could do something very similar and try and reparameterize a curve to the other curve to put them into correspondence. And if I do that for A to B and for font B to C, and then for C to A, then of course I have this consistency problem. And there's no reason why, if I go around that loop, that if I propagate my correspondences all the way around the loop, they should come back to the identity. And that can be a big problem, especially when you've got lots and lots of fonts, because now you've got a quadratic. Firstly, pairwise matching, you'd have to do a quadratic matching thing, or you have to sparsify the space and match along a tree or a DAG or something like that, and then you're going to be suboptimal because you don't know beforehand which the right way to build your tree is. And also, even if you do quadratically and then force some consistency equation, you've got then a massive outer optimization that has roughly the same number of parameters as this one as well.
Letter A, and you may not be able to come up with a good matching at all between...
Yes, so we'll come across that in just a second. So hold your thought for a few slides if you still have it. Shout at me again. So the way I sort of do matching is by just preparing the outline. So we take all the Bezier outlines, throw away the rest of the information. We normalize and align our polylines just to get them into the rough scale, the right scale, so we can look at curvature and things like that. And then we normalize to try and find the correct starting points, which is starting to cheat because I'm now doing something that I said that I wouldn't do, which is to start by pairwise. So we do a rough alignment based on pairwise matching, and at that point we assign each outline to a neighboring outline. We can't handle differences in topology, so we assume there's the same number of outlines. So I work out that the inner loop matches to the inner loop, and the outer loop matches to the outer loop. And if there are different glyphs, we'll see in a second with the G, we just throw that away and ignore that for the moment. And so once we've got these alignments, then we find these dense correspondences. So for each of the individual glyphs, we find the correspondences using an energy model. And once we've got that, gives us this parameter vector, which uniquely defines the shape of the font. And once we've got that, we can take this font and put it into a GPLVM, generative manifold, and find the mapping for each font, and then we can generate new fonts. So new locations in this manifold will then give you a parameter vector, and that parameter uniquely defines the whole of the font. So I'd start by talking about how to find the dense glyph correspondences. So the curve parameterization is very straightforward. We just take a sort of parametric approach with 0 to 1, going around a closed curve. So as you go from 0 to 1, you go all the way around the curve. And so if I take the first font, I would choose some specific values of t, and I will sample it you sort of uniformly sample it at t all the way around. So each t value then gives a point on the outline, so the t values define the polyline given the shape of the font. That makes sense. And then for the second font, I do the same, but with a different set of t values, and so on. With the nth font, I have a set of t values. And then my idea is that when I stack all these t values up, that I put the first one in correspondence, so the value of t in the first one corresponds to the same point on the matching point on the curve, and so on, all the way around. So by setting the values of this parameter t, I imply a dense correspondence across fonts. Hopefully that makes some form of sense. And then I have this very long t parameter, so it's about 512 points or something like that for each outline. Stack them all up and do an energy optimization on that. So what does that energy optimization look like? Well, we start. Oh, yeah, Matt.
Sorry. So, is this for every glyph that you're coming up with this set of t's?
Yeah. So each glyph shape is matched independently. In fact, each outline. So the outer outline has one set of t values that match. And the inner outline could be treated as a different glyph. In fact. Okay. So for the curvature matching, we're trying to say, we want concavities and convexities to be preserved. So we would have an optimization that tries to put corresponding points in areas of high curvature and low curvature. We have an elasticity constraint that says you shouldn't collapse all your points to a single point. They should be spread out around the curve. So that tries to encourage a uniform parameterization. We also have a special font-only bolt-on make-it-work extra term, which takes care of normal matchings on serifs, because there are some fonts where you can have a serif that stretches out massively. And so you have to sort of basically override your normal elasticity constraint. In some regions, you can let it massively expand, but that's special to fonts. And there's also a monoticity constraint in the fact that each of those t values is effectively a reparameterization. So the ordering of the t values must be preserved, otherwise you jumble them up. And that's the one that makes it a little bit tricky to optimize, because there's now a constrained optimization. So I put all this through in case someone asks difficult questions, because this is an audience where they might ask difficult questions. But I wasn't really going to go through the energy terms. Suffice it to say, that was the understanding that this monoticity constraint actually comes down to a linear constraint. So it's just a linearly constrained optimization, which makes it a little bit more simple as well. But the normal matching term, just sort of illustrate it, if you have a font with a really wide serif base and a very narrow sans font or something like that, and you use it without the normal term, and you look at the base bit there, you haven't quite, without the normal term here, you can see that the sort of correspondences are going up around the side of the letter, which is clearly not right. Whereas on the far side, the yellow and the purple dots at the bottom are allowed to expand outwards. So that's a little bit of a hack, but vaguely principled hack. And then we can just optimize all of that with nonlinear optimization. So all of those equations you can create analytic derivatives for them. And we solve with the linearly constrained quasi-Newton method, so using LBFGS updates. And if you do that, it doesn't quite work. And the reason it doesn't quite work is because of the monoticity constraint. And so we can see, hopefully, that the sort of the giant blue dot isn't quite in the same places across all of them, because it's clearly not a convex problem at all. We've got stuck in a local minimum, and it's because as you move a t-value, you've actually got to push all the smarties, or whatever you want to call them, in front of you as you reparameterize. And so pushing that through a big barrier like the concavity at the bottom of the A is really an expensive operation, and so you can't do it depending on how you initialize. But the answer to that is to do a course-defined approach. So if you take the elliptical Fourier components because it's a closed curve, and you go down to 2 elliptical Fourier components, then you basically have the combination of 2 ellipses. And so no matter how different A's are at the end of it, they all look the same like this, because they all eventually collapse down to just an ellipse. So if you start here and you match here, it's very easy to match because you have no strong concavities, and you can just go straight through. And then, of course, you use that to initialize the next solution, and so on. And as you go in, this guides you into a local minimum. And we found this is usually enough to make sure that you're always in the right sort of place. And so if we...
Can you say a bit more about the Fourier thing? Is it the basis for this linear basis for the space, or how
so just for the sort of elliptical one for a cocoa is just take the x. If you because you've got your t-value going between 0 and 1, you've actually got a Fourier series that just continues and continues and continues. So you just take a separate Fourier transform for x and for y.
You still need the 2D point correspondence, or do you still need to associate two-dimensional coordinates with these lines? Right?
But a single t-value for a given font, because you fix the. So once you've done if I give you a certain shape, you take the transform, and that gives you the fixed shape of the transform, and then I just reparameterize it by changing my t-values. So a new t-value then gives you a certain position within that curve, and that gives you the x and y.
So once you have the curve, I can see how this one-dimensional parameterization, how you can do stuff there, but how do you get the plots that you just showed? Right, these are curves in 2D space. What defines the 2D coordinates of the smarties? Or of the continuous thing? So I say I have a value of 0.7 on this curve, right? Yeah. So where do I draw the smartie?
So it's actually, you could do a Fourier transform where it's not evenly spaced. So like a standard Fourier transform, you have your samples evenly spaced in time, say. And so if I did a Fourier transform where my samples weren't evenly spaced in time, but were spaced at different t-values, that would give me a different Fourier transform, but it would be linked by the same equation.
Get the 2D coordinates? How do you decide where to draw the smartie? You showed just the plot where everything looks like a very small, like ellipse, right?
Oh, it's effectively just a smooth version if I took the curve and filtered it. So I took the curve, and it's always parameterized by t is 0 to 1, and I just filter it, then it collapses to be smooth, and then I do the Fourier transform in that space. Onto smooth space, which is effectively like doing the Fourier transform on the big space and then throwing away loads of the coefficients and just keeping 2, and that gives you a low. Yeah, sorry. Maybe it's easier if I draw. But this then guides you into by going all the way down this chain and reinitializing, you get guided into the right local minimum. So now you can see in the curvature bit, they all are in correspondence. And then the rest of it is quite straightforward. So for learning the manifold, we just use a GPLVM, Gaussian process latent variable model. So this is chosen because it's powerful and it has probabilistic and nonlinearities in it, so it's quite useful to be able to know the mapping, and it's generative. So we basically start with our high-dimensional vector, which are these. The high-dimensional vector aren't the t-values. Once we've optimized the t-values, we put the 2D coordinates back in again. So now when we're creating the manifold, you have actual 2D polylines that we're putting in, and we just say that is made up of some mapping from some low-dimensional space plus a bit of noise, and then our goal is to try and find the low-dimensional vector and find the mapping that takes us back into the high-dimensional space. So we take our particular glyph, we take our polyline samples in 2D, that give our xy coordinates as a big vector, and then we do that for all our other glyphs in a font, and then we stack all of those up as a massive vector, and comes to something like a 27,000 dimensional vector. And then we say clearly that 27,000 dimensional vector is generated by a 2D space, and so we embed that in some low dimensional manifold. And so these gray points are the points that the original training data come from. So each of those gray dots is Times New Roman or Arial or something like that. And then the heat map is the probabilistic variance of predicting. And of course, it's not actually 2D. I've just shown it as 2D, so I can draw it on the screen. But we have ways of using sort of Bayesian methods of ways of estimating the actual dimensionality of the manifold, which is, in this case, came much closer to 4. 4 was a bit of a kind of tweak it a little bit between 4 and 5 and things like that. But it's 4, and you can kind of see that in the structure, and that we've taken it and kind of unwrapped it. So you get these sort of islands of holes where you've sort of forced it to lie on 2D in this case. So roughly the predictive variance is telling us whether a font is likely or unlikely. It's a bit counterintuitive because in regions that are really unlikely far away from data, you just revert to the mean. So that actually gives you the average font. So it's not necessarily completely unlikely. But areas in the borderline, like away from the data, you're extrapolating more than you're interpolating. And that's a sort of dangerous territory. And then generating a new font is really simple. So we can take our sample on this point. That gives us a new low-dimensional location. We apply our mapping to it to get a high-dimensional vector, and then we can unravel the high-dimensional vector to get an entire font. In fact, that's the average font generated by this process. And so if we do that, as we move, because it's a smooth mapping, as we move smoothly, we can smoothly interpolate between all the fonts, and every point that exists in this space is a new font. And the closer you get to a gray dot, the closer you get to one of your training ones, and the further away you are, the more you've created a new font or something like that. But this is quite fun and incredibly addictive. I've got the, if I go sideways, will this work? Ooh, I'm going to break everything by doing this. Is that the right? Can we see that? No. Here we go. So everyone has the opportunity. You can do this so efficiently. You can even do it in JavaScript. So everyone has the opportunity to have a fun, if you are bored one day, if you go to my website, say we do F or something like that, you can see the individual ones and you can have a play. This is quite fun. And in no way wasted a good 4 hours when we first created this. Oh, sorry, yeah, sorry. What do?
Like, yeah, the blue.
So the blue, if you go right out the blue, this is the average. This is the average case. So you regress to the mean as you go very far away. So the borderline is where, let's see if we can find something weird. Somewhere around here, maybe. It's getting a little bit weird in the border, getting a little bit of wobble over here, maybe. Although part of it's also my lazy JavaScript rendering algorithm, which is probably not very good. And we'll see there are some, we can find, let's find something where it goes wrong. There's somewhere it goes wrong. I think capital J goes wrong. Somewhere. So we talk about this, there's some, yes, down here. You have this weird outlying font, so there aren't normally fonts with a massive bar all the way across. And there we need another extra serif term, because as you see going there, it's sort of curving here, rather than perhaps a more intuitive match would be just to shrink the length of the bar and things like that. So it goes a bit wrong down here. But that doesn't stop it from being OK up here. We're using an RBF kernel, so it's locally consistent.
Show small g.
Small g? Bjorn's anticipating a question. So you can see GE, and we can also see somewhere around here, alternate G, yes. It's not my first rodeo. So we'll talk about that in a second.
Just out of curiosity, is there any correlation between like popular fonts and between popular fonts and particular areas of density? Our popular fonts tend to be in denser areas, or are they more?
So yeah, I mean, it's quite interesting that we haven't really spoken to someone who's a super pro on fonts, but I mean the biggest divide is obviously sans to serif and things like that. But there is you can use it, and one of the ways of I'm always hesitant. So we presented it as a SIGGRAPH, and my main concern was that there would be someone who spent their lifetime studying fonts, and they would go, like, it's completely ridiculous that you would do that. And so obviously, it's not necessarily capturing all of the artistry of the font creation, but one of the reasons they thought, I actually spoke to someone afterwards, and they thought it was particularly useful, was exploration of places where they might wish to create a new font, because you start seeing things like Arial and Helvetica, and all these sort of fonts can be quite well clustered, and actually the variations that they're creating in there are pretty subtle. And so actually there's a whole sea of things here that you might want to go in and put your new font into.
And what about kerning?
Sorry?
Kerning?
Yes, so it's kerning and hinting. There have been works on those sort of things, and they can get quite close to doing a lot of that vaguely automatically. So I sort of sidestep again by saying I treat them as shapes and not as special fonts. Certainly hinting can be done, a lot of that can be done automatically these days. So you can also embed all the kerning information in, because it's a big vector, you can just concatenate any extra information on the bottom of your vector, and that will also be generated at the same time. So if you want spacing and things like that to go in, you can put that on the bottom of your vector, and you'll also get numbers that match the data coming out of the bottom of that. And so just to reiterate, when we do it jointly, I didn't show you the joint fonts, but if we do it jointly, every point is a full font, so you can obviously sample from an entire typeface just from a single point in the manifold. And now I've broken my magic clicker thing, or indeed PowerPoint, by doing this. Here we go. So every relation can be font, and sampling is a very fast process. So we've also shown there some individual font manifolds, so you can just show that, and these sort of show you the quality directly of the dense correspondences, because if your correspondences mess up, you have that thing like I showed you with the J going a bit wrong. So that's just some examples. So when we started this project, we looked at a number of different representations as well, and that the curve parameterization was really the key, and lots of people, and these sort of embody previous works in shape matching and things like this, like sign distance transforms obviously can handle lots of varying topology, which is good, but they have no constraint about it's very difficult to constrain topology, and so if you go from, say, Times New Roman to home or something like that, with your sign distance function, then unless your curves unless the sort of centroid line of the skeleton line of your curve always lies within the shape, you're going to come into problems. And even things like more intelligent things like Lagrangian mass transport, which are trying to sort of solve part of these problems, can't really cope because where the mass gets moved around from isn't very clear, and it's very hard to enforce any consistency in that. So this sort of, I think, the secret of it working is the fact that we represent as curves, and it's simple to it's intuitive to have this elasticity constraint and things in the curves that gives you good natural parameterization of the shape. And it comes, of course, at the cost of preserving topology. So yes, obviously, things can go wrong. Topology. So we are matching outlines, so we cannot match double bold G to single bold G because there are three lines, 2 lines. But I would argue, maybe I can sidestep the other way, but now putting a font hat on and forgetting that they're shapes, what does it mean to be halfway between these two? And I think you could argue, if you really had a high-level abstraction of how you might draw a G, you could say, well, if I draw a double bold G, and if I stop a little bit early, then maybe at some point there is an interim result that becomes a single bold G. But in general, in fonts, they actually have both of we can get around this problem because even if one font has a standard G, it has the other one embedded in it in its Unicode set somewhere. So we just use the right one to match. And the same is true for A, double stacked A and a lower stacked A. And I would argue there isn't really an interim case that would be a valid font, and we were sort of interested in valid shapes. Oh yes, and so here's, so that was where our failure matching was that we've got the whole height of that being matched, obviously, the crossway there, and that's not very intuitive. And so locally that corrupts the manifold. But it doesn't destroy the whole of the manifold, it just destroys that local region. Okay, so conclusion here is that we've sort of presented a framework for building this generative model of typefaces, and it sort of backed up, hopefully, what we thought was intuitive, was that fonts must lie on a low-dimensional manifold. So one of the reasons it works so well is that the number of rules that you use to design well-behaved fonts, like these fonts, haven't used crazy fonts. are a sort of relatively small set of rules, and therefore we can learn and capture those directly from the curves themselves without having to be explicit, which is good. Obviously, we haven't shown any crazy fonts that don't correspond to this with sort of magical extra twiddles and things like that. But again, that's sort of facing the problem of what would it mean to be halfway between, what does it really mean to be halfway between some font with sort of massive twills on the end of it? Can you sort of half the twill? Is that a valid thing? So the next level up in that requires quite a high level of high knowledge about fonts, and is also subjective about an individual font designer would probably say that halfway between the two is something different. But we can capture these rules from examples, and this whole process was entirely automatic. We just put in, we set some parameters in the energy cost function, but they're quite robust, and we just put the fonts in at the top and get the whole thing out at the bottom, which is quite nice. And so we haven't really begun to go into details about what we might use as applications for this. But also, the framework is reasonably generic. If you throw off the serif matching term, you can use it for matching other curves. So for future work, we would like to look at the topology limitations. Maybe a skeletal-based model would be more suitable, and try and extend beyond these standard fonts. There's also the option of, at the moment, the manifold is completely unstructured, so it's a completely unsupervised manifold. If we put some labeled training data, if we labeled some information about some of the fonts, could we then put that in and use that to try and give some structure to the manifold? That would be nice as well. Cool. So, oh yes. Yeah.
A typical problem with using a manifold representation is the dimensions of the manifold don't mean anything specific anymore.
Yeah.
So many different semantic concepts get confounded together. But you started with a very clear example where you wanted to make the font thinner or bigger, but you cannot quite do this.
So that's what I mean. Sorry, I won't can't go back. That's what I sort of meant when I went unstructured in this part of it. And so the moving from unsupervised to semi-supervised is putting that structure back in. And yes, so there's another area of stuff that we are working on, which is just general manifolds. How do you explore, as an artist, say, if you have a 5-dimensional manifold of shape space that are valid shapes, and I wish to create a new shape, so I take my existing one, I wish to edit it, and I'm basically going around one of those islands, and that I might have to move through an invalid shape in order to achieve a valid shape over here. And I think that is a very interesting area of work in terms of, and we'll touch on it again at the very, maybe we could talk offline afterwards, because if you have any ideas, because I'm very interested in that. The example, the final piece here, example, this final application makes use of exactly that, or we start to touch on that. Okay, so subspace appearance models. This is very old news. This is probably going back to before Jan LeCun started doing work on deep nets. But subspace models have worked very, very well when images are all aligned and have fixed structure. So I guess everyone is familiar with something like eigenfaces or Fisher faces, where if I take a stack of images that have all been, where they're all in correspondence, so all the pixels corresponding to the nose are in the same place, I can just stack them up, take off the mean, and do some PCA or do some factor analysis or LDA or something like that to give me a set of bases, and then load them up, and that gives me a parametric model that I can use to describe faces. And this works very well, but it doesn't work very well when objects can't be aligned. And so things like SIFFlow have done very well when there is a nice mapping, but if there's not a nice mapping, you can't align these data sets. So like a cat sitting down and the front part of a cat walking, there's no easy warp that would exist. And so building a subspace model in these sort of situations is very difficult. So there are situations where it can be aligned, and so active appearance models and gain lots of popularity with faces. So if I have some key points and I can bring these into alignment, I can find some dense warp. And once I've warped into alignment, I can then build my standard subspace model, and everything's fine again. But this requires some non-rigid deformation to actually exist. So it's not even that we have to just find the warp has to exist. And there are many situations where you can see that such a warp wouldn't exist. So if you have varying structure, or occlusion, self-occlusion, visibility changes, topology changes, different instances, there will be no nice, smooth, dense warp that exists to align these data sets. So my rather weird example is bunches of bananas. So here we can see that definitely each banana shares an apparent subspace, and that bananas you could conceive would lie on some subspace model of appearance, but there is no warp, especially one that's nice and smooth and realizable that can transform 3 bananas onto 1 banana, onto 2 bananas, onto 3 bananas again. So we can't make any of the assumptions that have been used to solve for things like deformation fields are not valid in these things. And this is not a rare case. This is, you often have to go the other way. You have to go out of your way to find things that have nice deformation fields. The standard case is not to have a nice deformation field. And so we're presenting all the C's A, which is context-conditioned component analysis. And so the idea is to say, well, even though we can't find a dense warp, correspondence does exist. So the red dots correspond to the end of the banana, the blue dots correspond to the front of the banana. And so if we go to some higher dimensional space where we put all the bananas in the same place, then we could build a subspace model where they all lie on top of each other and then unwrap that into a specific example of an image. And so this is the key is that we can find our correspondences implicitly by putting vectors into some context space. And I haven't said anything yet about what the context space is, but just some space that brings everything into alignment and does implicit correspondences. And therefore, the process to generate an image would be to take some form of structure map. We would then sample from this linear model into structure in the context space, and then project that down back into the, so from this, by finding for each pixel that image where it should have come from in the context space, we get a context vector, you go into the context space, and you look up that value, and you put it back there at that pixel. And so you can generate a new image. And so, as a sort of caveat, the way we're doing this with our inputs is that we don't just have the images now, we have what we call a part map. So our input training data for things like this is segmented images of horses or elephants or something like that, and at the moment, hand-labeled part map that we say this is a sort of, each part map corresponds to one thing. There's obviously ways we can go about now getting hold of these sort of part maps, so things like shape Boltzmann machines and things like that could be generative models for part maps. So it's a bit of a limitation at the moment that we need these part maps, but we have ways, other people's methods exist to try and get hold of these sort of part maps. And there's also discriminative methods that could be used to gain them. So just as a rough overview of related work, it's obviously far from exhaustive because loads of people have looked at subspace models. So loads of things have been worked on aligned subspace models, especially faces. And there's also the active appearance models and layered active appearance models, morphable models. And then there's also been some work on combining the parametric models with non-parametric models. So often subspace models, you lose high-frequency details by definition because you're going to truncate your eigenvectors. And so there's a way of using sort of image quilting or something like that to go in and reinstigate your high-frequency data from your low-frequency model. And there's also more interesting work is the sort of work on jointly estimating deformation and appearance. And again, there's some really nice work on this, but these also assume that there is some deformation field that can be applied. And so in the cases where there isn't a deformation field, this becomes a bit more tricky. So just to be a bit more concrete about it, the model is basically looks very similar to a standard subspace model. You've got a mean plus some set of bases, each with a factor loading h, and you've got some noise at the end of it. And then the trick is that, unlike a normal thing, we've got this extra vector c. So for every single pixel, we have this context vector, which tells us where in the context space. And then the thetas are our parameters that would normally be linear parameters. And we haven't said anything about the form of them, but we've also got these regression functions. So these regression functions take as an input the context feature and the parameter vector and give back a scalar. And so if we apply those, we get back to a normal subspace model, but we see that each mean vector and each basis loading is now dependent on the context, which means it's specific to each image rather than general. So if I could sort of illustrate that back the other way, we can see the normal PPCA, probabilistic PCA, is just a special case of this model. So if I set all the context vectors to be the pixel locations, then my mapping would not depend on the context. It would just be a mapping back to a simple linear transformation. And this model would then collapse down to just our standard PCA model, just like that with some noise. Or if we looked at that graphically, we could take our image, and our context space here would be two-dimensional, and it would just be the pixel coordinates, the 2D pixel coordinates that each pixel came from. And then we would just apply that grid. So if we pretended for a moment, and we'll say more about how we get this, but if we pretend that in the context space you have a continuous field, so these parameters define a continuous field, then the context space just tells you where to sample from. So if it was 2D pixel locations, you just sample of a 2D grid in your 2D context space, and that would then all give you the same thing as normal probabilistic PCA. Hope that makes some form of sense. And now we need to be a bit more concrete about how we define these mapping functions. So for tractability, because we can't store an infinite continuous field in the context space, we assume that the context space takes this form, which is that it's a linear product, but after some nonlinear mapping of it. So it's a linear product with the parameter vector after some nonlinear function A is applied to the context space. So this is a good choice because this linear projection means that lots of standard regression techniques can be expressed in this fashion. So you take some nonlinear function of your context space, and then you just do a dot product with some linear basis vector, and then your basis vector can be learned in the same way as a normal PCA. So if we take something like that, we would say, okay, any complex function, e.g., like any regression process could be used and put in this form. But the more common regression processes, things like basis functions, Gaussian processes, or something like that. In general, we choose sparse nonlinear projections because it makes the model process much more efficient. Because if you have a big context space, you don't want to store lots of things. So if we just use k nearest neighbors regression into this space, then we only have to store a sparse set of points in the field, and then that keeps costs nice and low. But in general, there's nothing to stop you from using any regression function you wanted from the space. And so this gets rid of our continuous field problem. So now we don't have a continuous field. So the general learning procedure now is that we say, okay, well, if we take our model like that, I could also express it if I just make it per image. So I is the image instance here. So I make per image. I have a different mu vector for each image, and it's because I sample from my context space. And if I take a different basis space from context, then I go back to my standard model like this. And then I could just write that as its probabilistic interpretation. So we just have it say Gaussian with some noise term just written on the end there, and we put a Gaussian prior on our factor loadings, all very standard normal PCA, probabilistic PCA approach. And then ideally we'd like to maximize, if we do maximum likelihood of learning or something like that, we'd like to maximize this log, but we have this big integral to perform that we can expand out into the hidden variables. And there's a number of possibilities for things you can do. And we probably take the simplest, which is just to replace the integral with a maximization. And then you can just alternately optimize for your hidden variables and for your unknown parameters. And that just becomes a special case of generalized EM with slightly more involved update equations, which will like this, but we won't go into. But it's just a case of standard EM once you've applied the context space. So the final piece that I haven't told you about is how you would get these context vectors in the first place. So the way we do it is we take our part labels. This is why we need the part labels, and we convolve them with some filters. So we take our part labels of each part, we convolve it with a filter bank, and we get these context vectors. So as a caveat, that what I'm showing here is quite hard to visualize them. I'm showing here is PCA having been applied to context vectors to go down, which is why you don't see the separate parts. But each one of those is effectively a dimensional. If I stacked each of those up on top of each other and then took it for a pixel, that would give me a vector, and that vector would be the context vector. And you can see it making sort of sense in that if I've got a leg like that and I apply a horizontal filter, I introduce a ranking across it, so I start to get like local coordinate systems in the part labels, which then imply some form of correspondence. And so we can do this for a variety of different shapes, and we choose different part models for different types of object. But once we've got that, we can learn our components. And so in the same way that the old subspace model assumed align factors, we can also calculate our means and our basis, sort of deformations among the principal basis. But in our case, they're now dependent on a particular context space. So each of these horses has a different structure map, which gives it a different context space. And so once you've given the context space, you can then calculate the mean, and you can calculate the deformations from the mean in the principal components, but they are different for each example because they use different context vectors. But they show standard mapping. So in terms of they're sort of consistent amongst one another. And so the way we can look at that operation happening is if I expanded out my sum there, so I start with my mean and my basis loadings, and effectively I go in and I fill in my context vectors for each of the spaces. I then do my k-nearest neighbors lookup into the parameter vector, and that gives me a customized mean and a customized set of basis vectors for that particular pose. And then it's just a linear combination of those factors, and go back to generate a horse. And so we'll show sort of how we could use this model on 2 example tasks. So in appearance transfer, we would fix the factor loadings for a particular horse and then apply those factor loadings to a context vector of another pose. And that would transfer. So the factor loadings encode fully the appearance, and the context vectors encode the shape of the horse. The same thing can also be done with structured inpainting. If we cut away part of the horse and we just learn the factor loadings on the bit that we observe and then use the structure map for an unobserved bit, we can then transfer those factor loadings onto the unobserved context vectors. And so in all of these cases, we are using the part labels to get the context. So we have access to we have a test and a training set in terms of learning the parameters of the model, but for every example in test or training set, we always need the part labels to get the context space. So this is what it might look like if we fix the factor loadings. I think there's 10 factors or something like that. Then the first line is the original data. The second line is the reconstruction under 10 factors. So it is the factors are capturing quite a lot of the appearance model. As we expect, you lose high-frequency content, but the basic low-frequency capture has been captured. And then we've picked our factor loadings onto the rest of the model, and hopefully all the horses have black tails or black rear legs and black necks going through. And we can do it with slightly more extreme pose changes. And so even from a weird cow horse or something in the third line, you can transfer the appearance. I haven't said how we do color. Color is just we have 3 factors for RGB, and we do estimate a rotation and translation to try and align the color spaces as we go. But it transpires that the Weissman horse data set is full of really bizarre horses, so the weird blueness isn't necessarily us. It's the actual original training data has, for some reason, a luminous blue horse in it or something like that. If you want to get really tricky, we can go to cats. And so this is quite fun because we'd only see the head of the cat. And so we fix the factor loadings just for the head and then transfer them across the rest of the cat. And so even though we've never set a factor loading for any of the body or something like that, we do know that the rest of the cat should also be black. And so we generate black cats by fixing the factor loadings. Yes, Matt.
So just to clarify something I thought I heard you say earlier. So all images, both training and test, have part labels, and they are used for this process?
Yeah, so they use that gets the context space. And so we need the context space for each of them. And so so maybe that's deceptive, actually. We should probably, so the purple isn't really purple. The purple is the unknown region, but I do have the part labels for those unknown regions. But of course, then I can do structured inpainting in the same fashion.
So the parts are always observed?
Yeah, so I observe the parts. And some quite challenging ones with cats, but it's now, we've been struggling a bit, actually, if anyone has any comments afterwards, we've been struggling a bit on ways to really identify how well we're doing, because it's a very difficult problem to actually judge how well you're doing when you're doing appearance transfer and things like that, because you don't have a data set of what the horse would look like in that other pose. So maybe we need to go and make that data set of horses in different poses. So our limitations are, as with all of them, we lose these high frequency details, but we could come up with image quilting or something to combat. There is this problem now of this context generation is inconvenient. So we use a fixed function for the context vector. There's no reason to suggest that that was the optimal one, and there's no reason to suggest it's not in any way overcomplete, maybe using far too many filters. So there's obviously lots of room for learning. We could learn the context space directly. We don't necessarily have to go via a part map. That was sort of as for convenience rather than anything else. And so the final just little example I was going to show is this application of sketch synthesis. So if you don't like fonts, you can still build nice manifolds that match things, but you could build them for something like elephants, which is much more fun, say, than fonts. And if you really don't like elephants, everyone loves cats, because the internet is full of cats, so you can also build some of these models for cats. And you might notice some of these red shapes wandering around the manifold. And that's because in this particular application, we're teaching to draw. So one of the ways you're taught to draw is with these masses, so ellipses. So you sort of sketch out the masses of an object to give you the right pose, to fix the pose and get the proportions correct. And once you've got your masses correct, you go in and fill in the contours and all the high details. And so in this particular framework, our goal was to say, okay, so you have a tablet and you're going to draw, you can sketch, draw your masses, and it's going to give you feedback in the forms of these color ellipses as to where you might want to put those masses. And it lets you move them around, and as you move around, these shadows will change to suggest where you might want to draw. And then once you've done that, it will also help you with the outlines. It will suggest where you might want to draw your outlines. And once you fix your contours and your masses, you can pick some. We haven't really done very well on that part. We just gave a palette or something like that. You pick a particular palette or something like that, and then you go and you generate a photorealistic horse. It's probably too dark to see. Oops. But the idea being that all of this process, all of the data in this process is learned from actual images. So it's not encoded. And unlike things like shadow draw, we don't just sort of return you some nearest neighbor images to suggest what you're doing. We're actually interpolating in the space and coming up with suggestions. So the idea is it's sort of customizable clip art. If you have in your mind what you want to create, we can make you the horse in that pose. And so, again, our training data is similar. We use our part labels again. And then from those part labels, we determine our masses. And then we also take the outlines of the silhouette. And we find some correspondence points just to normalize the outline. And then those two are the inputs that we learn in our manifold, put into the manifold. So that goes into the manifold, and you can build your manifold as shape. And now you can do things like, if I start querying where the ellipses are, if I fix the ellipses, I can go into the manifold. And this, I guess, is maybe answering your question. So you can start by doing an optimization. You start with a load of C points around a whole space, and do an optimization of trying to locally find parts that look more closely to your ellipses. So this gives you a load of modes that have very similar ellipses on or valid ellipse configurations that we have on the manifold and the corresponding contours. And so once you've done this, you can get some feedback, and then you can. And so for this example mode, you see we've always got an outline that's in the right pose, and we also have some neighboring images that we get from that as a query. And so those we can use to learn models to generate local good when we come to the texture synthesis part. And so the way we do the final thing is actually image melding. So this is before we did the appearance model. So we actually take some features from the ellipses and the contour and use them to guide patch matching. So we take neighboring images that we know in roughly the similar poses, and we warp them and then blend them with different weights and warp them together by combining two horses together, but in the right pose. Cool. And so by now I'm fed up of looking at horses and cats and elephants. We added pigeons in as an extra bonus option, which are also really annoying to look at large data sets of. So in conclusion, this manifold can provide intelligent feedback. We're not just showing the nearest neighbor results. We're actually creating new ellipse configurations and contours that we've never seen before in order to provide this feedback. And so we can therefore generate novel poses, but poses that are validated by the data. So we're not doing procedural modeling. We don't have to write down the rules. All of these rules are learned from data sets. And at the moment, the limitation of this one is the appearance model only supports nearest neighbors. So we can't, if you don't have any training data locally of horses in that pose, we can't warp them. And obviously we're looking at using our previous stuff to try and overcome some of those limitations. And we still have this problem of labeling the training data, but that's, again, going to be dealt with, hopefully, in the same way that a shape bolts machine or something can do the generative model part of that as well. So, for the future, in conclusion, so it'd be nice to have, for all of these, there's always been a stopgap at some point. So we'd like to have end-to-end learning, say, for the context space and everything like that. So you go straight from your silhouette to the final appearance model, learning how to generate the context space in between. That would be nice, and we'd like to combine properly all these generative models of shape and appearance instead of having interim stages. And also, I mean, ultimately, if we're doing graphics applications, we want the best possible image quality. So we need to look at that as well. And as also, all of this has been 2D, but lots of it can equally apply in 3D. I'll talk about this with you guys individually. Darren asked me to put this in as PR for Bath because we've got this new grant from the EPSRC we've got a load of money for motion capture, so 5 million. We've got a whole Vicon system and some 4K cameras and things like that, looking at motion capture with people in health and sports, as well as VFX and augmented reality and VR and things like that. And we're keen to collaborate with anyone who's interested in getting lots of data. We're trying to make a system that can go outside as well to get some outside. And we've got lots of students who are going to be coming up in September and working on it. Cool. And just to thank Daniel was the PhD student at UCL who was working on this, and the context correlation analysis was worked with Simon and Jan, and the sketch-based one, Dan Goldman, was Adobe was the guy who came around doing the sketching, and lots of this was started with my former boss at UCL, Jan Counts, who's now in video research. But thank you very much indeed.
So you showed that these context spaces for the horses, for example, were manually defined, and this makes a lot of sense, right? We humans have a good intuition for that. But there may be many applications where you would be willing to make this annotation during training time, and then giving a novel image, you want to do this fully automatic. And in the example you showed of the horses, how much does it deteriorate visually if you, for example, corrupt the label maps, the context maps, or
if you got the context wrong.
Regress the context maps just by using some learning.
So we haven't done those experiments, but we haven't got them in the paper yet. But the thing we are working on next is doing effectively that by, if you say something like the shape bolts machine, we train that. So we use our labels at the training time to train that, and then you condition that, say, on an input silhouette. And so you have to specify something if you want to generate. So either it's purely generative and I just click a button and say I want a new horse, in which case you can sample whatever you want, or you have to specify something somehow. So either part of a silhouette or a full silhouette. And then you would condition the shape bolts machine, the part shape bolts machine on that silhouette. That would effectively give you your context space, or you could learn it the context space rather than the part labels. And so that's, we've been talking to Ali a bit about doing this, and so that's kind of the next step. And then I'm trying to find the data to be able to answer that question. But you're quite right, I could just corrupt the part map a bit and have a go. We haven't really tried. Doing that.
Semantic segmentation task, have separate.
Or use one of the discriminative, because there's also part discriminative classifiers for part labels. Yes, so we could try one of those and see how that came.
Great. Cool. Well, let's thank Neil again.